This is the last module on radiation. It's based on chapter 13 of your ebook. This is the first part of the last module. This module covers view factors, radiation heat transfer between surfaces, and radiation network. Now, previously in the first module on radiation, fundamentals of radiation, we look at the radiative properties of a surface. But the surface is not alone. The radiation exchange occurs between a surface and other surfaces around it. So, radiation exchange between surfaces depends on orientation of the surfaces relative to each other, radiation properties of the surface, emissivity, reflectivity, absorptivity, and transmissivity. And radiation exchange also depends on temperature of the surfaces. Now, earlier in the first module, it stated that it's not easy to get the reflectivity, absorptivity, and transmissivity. However, using Kirchhoff's law, we may solve for at least the absorptivity by knowing the emissivity if we make an assumption that the surface is gray and diffuse, which means it's independent of direction and wavelength. And of course, the temperature of the source of irradiation is approximately, if not the same, as the surface temperature under study. It's given by 1247 Kirchhoff's law. The dependence on orientation is accounted for by the view factor F. Now, the view factor F subscript Ij is defined as the fraction of the radiation leaving surface I that is intercepted by surface J. J is the interceptor. The view factor is also termed the configuration factor or shape factor or angle factor. So here we look at how view factor is schematically described. So we have here surface I. Some of the radiation leaving surface I is intercepted by surface J. The others are intercepted by other surfaces. So this is radiation exchange between elemental surfaces of area DAI and DAJ. Both surfaces I and J are assumed to be diffuse emitters. The radiosity J, which is the emission and reflection of surface AI, is assumed uniform in all directions. The total rate at which radiation leaves surface I in all directions is just given by 13.5. See, multiplied by surface area of I, the radiosity multiplied by surface area. Now, from the definition of the view factor, that is the fraction of radiation leaving surface I and intercepted by surface AJ. So we have the definition of view factor in the form of an equation given in 13.8. For any arbitrary surface I and surface J, which are diffuse emitter and reflector with uniform radiosity, we have what we have reciprocity relation, 13.10. It's very convenient and is used frequently in radiation analysis. For surfaces in an enclosure, conservation rule applies. We have now summation rule, 13.12. Means the fractions total up to unity. As you can see here, conservation, we have n surfaces. Now the fraction of the radiation leaving surface I, total up, intercepted by all the other surfaces, including itself, must equal to 1. If the surface is concave, as shown here, concave, now Fii, that means the fraction of radiation from surface I intercepted by itself, is not 0. If the surface plane is convex, then the fraction of radiation leaving itself intercepted by itself is 0. For radiation exchange with n surfaces, we need n to the power of 2 view factors. Can you see why? But fortunately, not all the view factors have to be determined directly. N of those view factors may be determined from the summation rule. Meanwhile, n minus 1 over 2 view factors may be obtained from the reciprocity relation. So we only need n minus 1 over 2 determined directly. For an enclosure with 3 surfaces, how many view factors do you need? It's just 3. View factors for certain geometries are given in tables 13.1 and 13.2 as well as figures 13.5 through 13.8. So here in this table, we have aligned parallel rectangles, the relation to get the view factor, coaxial parallel discs, and perpendicular rectangles with a common edge. And for this figure, if you know the ratio of L2 over D, it intersects the line of L1 over D somewhere here, and you may determine your view factor reading it across. It's not as accurate as having an equation to represent the view factor. For radiation from surface I that is intercepted by surface J, which consisted of several subdivisional end surfaces, so we have 13.13 superposition rule. So here, I think this diagram clearly describes what's meant by superposition rule. Like you have an infinitely long channel with cross-section as shown. So the view factor from I to J is just the summation of view factor of 1:2 plus 1:3. Next is the symmetry rule. Applies for two or more surfaces that possess symmetry about a third surface will have identical view factors from that third surface. So that means view factor from 3:1 is the same as 3:2. Now the presence of symmetry can only be determined by inspection, of course. You apply the reciprocity rule with the symmetry rule. View factors from infinitely long surfaces are the cross strings method. Many problems encountered involve geometries of constant cross-section which is very long in one direction relative to the other direction. For instance, channels and ducts. Such geometries can be considered as two-dimensional with negligible end effects. The view factor between their surfaces can be determined by the simple cross strings method. So the surfaces of the geometry do not have to be flat. It can be convex, concave, or any irregular shape. So if you have two surfaces, you label one as 1 and the second as 2. And then you connect the endpoints of the surfaces with tightly stretched strings. Also crossing. So the view factor then can be written in terms of the lengths of the strings. This is what Hotel's cross-string method. So the view factor from surface I to surface J is just the summation of the cross strings minus summation of the uncrossed strings divided by twice the length of string on surface I. It's quite straightforward, and you can apply this cross strings method when the two surfaces share a common edge, as in a triangle. So the common edge is treated as an imaginary string of 0 length. You can try that out using the Hotel's cross string method to get the view factor. So the cross strings method can also be applied to surfaces that are partially blocked by other surfaces by allowing the strings to bend around the blocking surfaces. Radiation heat transfer from black surfaces, ideal surfaces. For two black surfaces of arbitrary shape maintained at temperatures T1 and T2, the net rate of heat transfer from surface 1 to surface 2 is given by 1318. Now previously, when you look at the single surface, you would have only the first term. So the area multiplied by the black body radiation, and the view factor is just 1. Yes. So now you have interaction between two black surfaces. Applying the reciprocity relation, yes, it will yield 1319. A negative Q, and this heat radiation exchange between surface 1 to 2 means the net radiation from surface 2 to surface 1 if it's negative. For an enclosure consisting of n black surfaces, the net radiation heat transfer from surface I to each of the surfaces in the enclosure is given by 1320. So if you look at the net radiation to itself, so this will be Ti. How about for a concave surface? For a convex surface? Radiation exchange between opaque, diffuse, gray surfaces in an enclosure. Surfaces in an enclosure often simplify as opaque, diffuse, and gray, which means that they are non-transparent, diffuse emitters, diffuse reflectors. Radiation properties are independent of wavelength. Each surface is isothermal. Incoming and outgoing radiation are uniform over each surface. Yes, that is, if the surface is opaque, diffuse, and grey. Now, from the definition of radiosity, summation of radiation emitted by surface and radiation reflected by the surface, we have this equation. For an opaque, diffuse grey surface, we apply Kirchhoff's law. That is, the reflectivity is equal to 1 minus absorptivity, because the transmittivity is 0. But you know the emissivity, so you can get the reflectivity from this relation, and you substitute it in, you get 1321 in watt per meter squared. For black body radiosity emissive power, you just have 1322. Yeah, J is just alpha T1 to the power 4, T in Kelvin. Now, radiation may leave an opaque surface, I, due to both emission and reflection from irradiation. Yeah, no transmission. This radiation, upon reaching a second opaque surface, J, may be absorbed or reflected. The net radiation leaving surface I is the difference between the surface radiosity and irradiation. Solving for the irradiation from 1321, 1321 there, and substituting into 1323, you get 1324, which, if rewritten in this form, will give you surface radiative resistance. Remember the thermal resistance equivalent network in chapter 3 of the ebook. So this term in the numerator is the driving potential. If the emission exceeds that of its radiosity, positive QI, there is a net radiative transfer from the surface and vice versa. So schematically shown here, I like this figure because it describes the interaction, the radiation interaction. So radiation exchange and an enclosure of diffuse grey surfaces with non-participating medium. Yeah, so this is just a schematic of the enclosure. This is a radiative balance. We have irradiation and also emission and radiosity. And C is the radiative balance according to 1324. Well, this is the equivalent element, equivalent network element representing the net radiation transfer from a surface. So you have this resistance as described by 1326. Some surfaces in practical heat transfer applications are modeled as being adiabatic since their back sides are well insulated and the net heat transfer through them is zero. These surfaces are said to be re-radiating surfaces. So you have this equal to 0 where the denominator is disregarded, no net heat transfer through it, and you have just the radiosity being equal to the black body radiation. Now, the temperature of a re-radiating surface is independent of its emissivity.